Hello friends, today we are going to learn mathematical optimization. Mathematical optimization is the selection of best element or best solution from some set of available alternatives. Optimization problems of sort arise in all disciplines from computer science and engineering to operational research and economics. In the simplest case, you can say an optimization problem consists of maximizing or minimizing a real function by systematically choosing input values from within an allowed set and computing the values of the function. In today's video, we are going to learn how to minimize the objective function by using Simplex Big M method. We will take this example for minimizing the objective function. We have to solve this example by using Big M method. First of all, we will learn how to solve this example by using simplex algorithm. Actually, there are three important stages in the simplex algorithm. They are called initialization, iteration and termination. Now, under initialization, the algorithm starts with basic feasible solution. In the right hand side, values are always non-negative. So, when we start solving a problem using the simplex algorithm, the first thing we need to do is to have the right hand side values non-negative, and then as we construct the first simplex table, we have to make sure that the simplex table has basic feasible solution. Now the algorithm goes through sub-intermediate iteration, which is called iteration, and the algorithm terminates when there is no entering variable and it provides optimal solution, which is called termination. Such type of examples, first of all, we have to convert a minimize function into maximize one. It's only for simplification. For that, we have to multiply the objective function with -1. That's why it becomes z equal to -6x1 minus 8x2 plus 0s1 plus 0s2 minus ma1 minus ma2, subject to some constraint. Now we can see here they have given greater than equal to sign. So at that time we have to introduce negative slack variables to convert a greater than or equal to inequality into an equation. Also makes these negative slack variables greater than or equal to 0. That's why if you want to remove this greater than equal to sign, we have to add surplus variable, which is nothing but negative slack variable, that is minus s1. Similarly, we can add in the second equation, because also in second equation greater than equal to sign, so we can write minus s2. But for basic feasible solution, we are adding two artificial variables in the constraint equations, which is nothing but plus a1 and plus a2. Now you can see on the right hand side we have the positive values, that is non-negative values. Okay, this is also important. x1, x2 and the slack variables should be greater than equal to 0 in the final solution. So in this way we can convert this minimize question into maximize one. Then what is the procedure we have to adopt for the Big M method? So first of all we have to write the LPP in standard form. It means when we are having the symbol greater than equal to, at that time we have to add surplus and artificial variable, like that we have added in last slide. Suppose we don't have greater than equal to sign, but we have the equal to sign, then also we have to add only artificial variable. At that time there is no need to add surplus variable. Okay, that is the first step you have to follow. In second step, in the objective function, assign a very high negative coefficient for each artificial variable. It means we have added minus m value, okay, which is having a very huge value or up to the infinity, because this maximum value or big value of this m, that's why it is called as the Big M method. Very high negative coefficient for each artificial variable. So we have added minus m and minus m to these two artificial variables. Then we can apply the simplex method for the above LPP standard after converting all the inequalities into equalities. Now we will make the first simplex table. So we have to draw this simplex table. Okay, it the number of columns and rows depends on your basic variables and then decision variables. Now here, first of all, we can write x1, x2. These are called as decision variables. So we can call this x1 and x2 from these constraints or from the objective function. Then we can write the surplus variables, which are nothing but s1 and s2. So all these variables you have to write from the objective function. The next one, these are the artificial variables a1 and a2. We can also write RHS because in constant equation RHS is given. So coefficient of all these decision variables, slack variables and artificial variables we have to write in tabular form. First of all, we can write from the objective function coefficient of x1 is -6. Similarly for x2, that is -8. For s1, 0. For s2, 0. For a1, -m. For a2, -m. There is no RHS value, so we can keep this last cell blank. Similarly, for the constant equations, first of all we can write here from the first equation the coefficient of x1, that is 2. You can write here 3, then -1. Then there is no s2 value in the first constant equation, so we can write 0 here because s2 is not appearing in the first equation. Similarly for a1, a1 is there in the first equation, so you can write 1, and a2 is not coming in the first equation, so we can write 0. So RHS of the first equation is 7, so you can write 7. I repeat, you have to write all these numbers from this first constant equation. That's why I can write here 2x1 plus 3x2 minus s1 plus 0s2 plus a1 plus 0a2 equal to 7. Similarly, for second constant you can write 4, 5, 0, -1, 0, 1, RHS is 9. Now we have written all these expressions, all these equations in tabular form. That is the first simplex table. Later on you have to find which are the basic variables. Now you have to write the basic variables. It means your answer or your objective function should be feasible. For basic feasible solution, we have found basic variables are a1. Okay. Now what is the coefficient of basic variable? You can write on the left side CB, that is the coefficient of basic variable. You have to write it from the objective function, that is -m. Similarly, there is another basic variable which is nothing but a2. The coefficient of basic variable is also -m, so you can write -m. For finding the leaving variable and entering variable, we have to add 2 more rows in this table. So I can write first of all zj. Okay, so what is meant by zj, or how to calculate the value of zj? For that we have to multiply the coefficient of basic variable, that is -m, with the decision variable coefficient, that is -m into 2 plus you can write -m, that is the coefficient of the basic variable, and in the second row -m into 4. So you will get -6m. So I repeat, -m into 2 plus -m into 4, you will get -6m. Similarly, for the next column we can write -m into 3 plus -m into 5, so you will get -8, -8m. Okay, then we can write cj minus zj. It means this is your cj value, so you can write -6. We can write here -6, then minus in bracket of -6m. So we will get -6 plus 6m. That's why we can write 6m minus 6. That's why we will get 6m minus 6 in the last row. Similarly, for the next, we can say -m into 3 plus -m into 5. So we'll get -8m. You will get -8m. Then you can write here minus 8 minus 8 minus in bracket minus 8m. So you will get 8m minus 8. That's why I can write here now 8m minus 8. Similarly, for the next columns, you will get minus m into 1 plus minus m into 0. So you will get m. Then 0 minus m, you will get minus m. Similarly, for the next things, you will get minus m into 1 minus m. So minus m minus minus m, you will get 0. So mm gets cancelled because m is not the constant, it's the big number. That's why we can write 0 here. In the last column, then minus m into 0 plus minus m into 1, you will get minus m minus m minus minus m. So mm gets cancelled, you will get also 0. Similarly, for the RHS, we can also write RHS, but in the final solution, artificial variable should not come. Now here you can say artificial variable is coming. That's why we have to construct the next table. Now we have to decide which one is the entering variable and which one is the leaving variable. For finding the entering variable, we have to select the maximum positive value from the Cj minus Zj. This is very important. From the last row, you have to find which one is the maximum positive. Here, suppose we are considering m is a big number. Suppose we are considering m is 1000. So we can put 1000 instead of m and find out the values of all the cells. So you can see at that time 8m minus 8 is the maximum positive value. We can also say the coefficient of m is maximum, that is 8. That's why 8m minus 8 is the maximum positive value, that is called as pivot column. Okay, and now entering variable is x2. Now for finding the leaving variable, the entering variable, okay, x2, that is called as pivot column. Now for leaving variable, find ratio. We have to add one more column here. So we can write ratio here. And how to find out the ratio? So for finding the ratio, you have to RHS divide by the pivot column element. Now it's the 7 divided by 3. So you can write here 7 by 3. You will get 2.33. Similarly, for the second row, we can write 9 divided by 5. You will get 9 by 5, that is 1.8. Then for finding the leaving variable, find out the minimum value, okay, from this ratio. Now you can see here 1.8 is the minimum value. That's why now the second row is the leaving variable now. It means you can say x2 is the entering variable and a2 is the leaving variable. That is the first table of the simplex method. Now for the second table, that is the iteration, phi is the common element. Okay, that's why this phi is called as pivot element. This phi is called as pivot element or key element. So for the next table, we can copy the same table as it is from the last slide. Okay, so I am not changing anything here. This is the entering variable with the leaving variable. So I can copy the same table. This is the pivot element, all of you know. I am copying the same table below the first table. And a2 is the leaving variable. I am writing the same values from the first table. So a2 is the leaving variable, so a2 should leave. And instead of a2, which one is the entering variable? x2. So x2 will come here. So what is the coefficient of the basic variable x2 from the objective function, which is nothing but minus 8. So you can write here minus 8. This is the second row. Just for simplification, I can write this is the R2. It is my second row, and the first row you can say it's R1. Now we have to make this pi as 1. That's why I can divide the second row with pi, with the key element or with the pivot element. That's it, R2 divided by pi. So in calculator you can save this function, that is b upon phi. The second row I can call it as b. I can say alpha b divided by phi. Calculate. So what is the value of b here? First of all, so equal to 1. So I can write here 1. Similarly, in the another cells, so what is the value of b? That is 4. So I can write b is 4. So we'll get 4 by 5, then 0 by 5, then minus 1 by 5. So similarly we can calculate the other values. 4 by 5, 0 upon 5, 0, minus 1 by 5, 0 upon 5, 0, then 1 by 5, and RH is also 9 by 5. Similarly, after converting this pivot element as 1, so above the pivot element you have to make this element now as 0. For that I can write R1 minus 3R2 in the first row, this is the second row, then you will get 0 at this place. For in calculator I can write a minus 3b, it means R1 minus 3R2. So same formula in your calculator. I can say alpha a minus 3b. We can say calculate. So what is the value of a? That's the first one, that is 3. So you can write 3 equal to, what is the value of b? That is 1. That is the new value of the second row, that is the 1. So you will get 0. So you can write 0 here. Similarly, for the next values you will get minus 0.4. So what is the value of a? That is 2. So you can write 2. So what is the value of b? That is 4.4 upon 5. So minus 2 by 5, which is nothing but minus 0.4. So I can write here minus 0.4. Similarly, for the next cells you can write minus 1, 0.6, 1, minus 0.6 and 1.6. For finding the entering variable and leaving variable, we are calculating Zj. Again, for calculating Zj, we have to multiply minus m into 0.4 minus m into minus 0.4 plus minus 8 into 4 by 5. Then you will get 0.4m minus 6.4. Then Cj minus Zj. What is the value of Cj? That is minus 6. So minus 6 minus 0.6m minus 6.4. If you are simplifying this equation, we will get, before that, first of all I am calculating the full all the values of Zj. So we'll get second minus m into 0, 0, minus 8 into 1, you will get minus 8. Similarly, for the next one, minus m into 1, that is minus m, plus 8 into 0, you will get m. Okay. Similarly, we can write all other values, that is minus 0.6m plus 1.6, minus m, 0.0m minus 1.6. Then for calculating Cj minus Zj, we can write here now, that is minus 6 minus, again in bracket, 0.4m minus 6.4. Okay, so if we are making this minus 6 plus 6.4, you will get 0.4. Thus we will get minus 0.4m plus 0.4. Similarly, for the next rows you will get 0, that is minus 8 minus minus 8, that is minus 8 plus 8, 0, minus m, 0.6m minus 1.6, 0 and minus 1.6m plus 1.6. Again, for finding entering variable, find out the maximum positive value from the Cj minus Zj. So you can see here this m is having negative coefficient, so this is not the maximum positive. The 0 value is also minus m, so we have to find out which value is maximum positive. You can see here m is having positive coefficient, so 0.6m minus 1.6 is the maximum positive value. Now this is your entering variable. Okay, similarly we can find RHS. Now this is the entering variable. Now for leaving variable, you have to find out again the ratio. Maximum positive value we have marked it. Now for ratio, again RHS divided by the pivot column value. So 1.6 upon 0.6, you will get 2.667. Similarly, for the next row, 9 by 5 divided by minus 1 upon 5. So we'll get minus. Now out of these two value, if you are checking, now you can say, anybody can say this is the minimum positive. Okay, but remember one thing, you have to always check the absolute minimum value. So if you are checking out of these two values, 2.667 is the minimum value, because we are checking absolute minimum value. That's why 2.667 is the leaving variable now. So this is first row. Now this row is called as, now this row, this is the pivot row. You can see 0.6 is the common element, so this is called as key element for the next table, for the next iteration. So 0.6 you have to make it 1, and below 0.6 you have to make it 0. So we can do these things in next table. See, we have written the same table as it is from the last slide. So 0.6m minus 1.6 is the entering variable, is the leaving variable. Okay, this is called as key element or pivot element. So we have to make this pivot element as 1 by dividing with the same value of the pivot. It means we have to divide the first row by pivot element. So we can write the same table in the below. We can write now here x2. All of you know the x2. What is the coefficient of x2? That is minus 8. Then which one is the entering variable? So s2 is the entering variable. So instead of a1 we can write here s2. So what is the coefficient of s2? That is 0. So we can write here 0 here. So you have to make it 0 here. Okay, that's why I can write r1 divided by 0.6. In calculator you can write a divided by 0.6, so you will get 1 here. Okay, similarly you will get minus 0.4 upon 0.6, 0 upon 0.6, minus 1 upon 0.6, 1 upon 0.6, 0.6 upon 0.6 you will get minus 1, and minus 1.6 upon 0.6. Similarly, below the pivot element you have to make it 0 at this location. That's why, how to make it 0 here? For that I can write r2 plus 1 upon 5 into r1. So in calculator we can save these things. So r2 is the second row, that's why I can write b plus in bracket 1 upon 5 alpha a. So you can say calculate. So what is the value of r2? R2 is minus 1 upon 5. You can write minus 1 upon 5. So what is the value of r1? So at that time you have to always take the new value of r1. So new value of r1 is 1. So you can write here 1. So we'll get 0. So I can write here 0. Similarly, if we want to calculate for the next value, we can write R2. What is the value of R2 here? For now, for this, so R2 is 4 by 5, 4 upon 5. What is the value of A? So we have to take the new value of A, that is minus 0.4 upon 0.6. So minus 0.4 upon 0.6. So you have 2 by 3, which is nothing but 0.6667. You can see here, you will get 2 by 3. Okay, similarly for the next values, you will get 1 minus 1 by 3, 1 by 3, 0, 7 by 3. Then again, for finding the optimal solution, again we have to calculate Zj, which is nothing but 0 into this value, which is nothing but 0. 0 into this value plus minus 8 into 2 by 3. So you will get minus 5.333. Then next one, 0 into 0 plus minus 8 into 1, you will get minus 8. Then minus 8 into minus 1 by 3, you will get 2.6667. Then you will get 0 minus 2.6667, 0. Okay. Now forget about RHS. Then we will calculate Cj minus Zj. Now Cj minus Zj, it means minus 6 minus 5.333. So we will get minus 0.6667. So I repeat, if you want to calculate, you can write minus 6 minus, get minus plus 5.333. So we'll get 0.6667. Next, minus 8 plus 8, 0. 0 minus 2.6667, that is minus 2.667. 0 minus 0, you will get 0. So minus m, you will get minus m plus 2.667 and minus m. And you will get Zj, that is 0 into this value. Okay, that is 0 into this one plus minus 8 into 7 by 3, you will get minus 18.667. Then again calculate which one is the living variable and which one is the entering variable. For that, first of all, find it where is the maximum positive value. In the last row there is no maximum positive values, or you can say all values are negative. Now the algorithm terminates because we don't have the entering variable. Okay, and for the living variable there is no need to find the living variable because there is no entering variable. So we have to stop your solution, or you can say the simplex method terminates when in the last row Cj minus Zj maximum positive value, or all values are negative. When all values are negative in the Cj minus Zj, we can stop the iterations and we can write the optimal solution. Since all Cj minus Zj is less than or equal to 0, you can say optimal solution is reached or optimal solution is arrived. Now we can read the decision variable values. So x1 is not comes in picture anywhere, so you can write x1 is 0. Okay, because it's not anywhere, so you can write x1 is 0. What is the value of x2? So x2 is nothing but 7 upon 3. Okay, which is nothing but 2.333. And value of, remember how to read, so x2 value is 7 by 3. Value of Zj is minus 18.667. So there is no x1 value, that's why I can write x1 equal to 0. So what is the value of surplus variable? S2 is nothing but 1.6 upon 0.6. But for the original problem, we have multiplied with minus 1 for converting minimizing question into maximization. So again we have to multiply this objective function with minus 1, and then we can write the final solution is minimize, that is the objective function is minimize z equal to 18.6667. That is the final solution. Thank you for watching my video on my YouTube channel. If you are having any questions, you can put in comment box.